Alright, today's lesson is strain potential energy. You'll notice there's elastic in brackets there. It's also known as elastic potential energy. So, in current study design, they use the word strain instead of elastic. I'm not really quite sure why, but people who write the study designs have their ideas about things. So, when we've got a spring, for example, so here's a spring, there it is, nice spring. If we were to then stretch that spring out like so, we would have then changed the length of the spring by a certain amount. So to do that, we would have to apply force, and so we've done some work. So then the spring itself, and this is where the strain potential energy is, so this spring here that's been stretched, if I stick something there and let it go, it's going to spring back. So hence the potential energy. So the strain bit comes, I guess, it's under strain when it's here, and the elastic bit is because it bounces back. So interchangeable, just terminology. Anyway, so the energy stored would be equal to the spring potential energy, which would equal the work that's done on the spring. All right, and so back in, as it says in your notes, 1675, a guy named Robert Hooke actually investigated springs, and what he found was that if you have a spring, there it is, and we stretch it a little bit, it would require a certain force to do that. But if you stretch it more, it needs more force. And so what Hooke came up with was this, that the force required to stretch a spring by some amount is related to some constant, and the force required to do it, or the force on the spring, is negative. Alright, so this is the force that the spring exerts, and the delta, the negative here, indicates that, well, the force the spring provides is going to be in that direction, but the actual distance that you've stretched it is in the opposite direction, so that's all that negative means. So the force is negative some constant times by the amount you've stretched it. So if we graph that kind of thing, which we can quite easily do, what we get is something like this. So we get a straight line graph, and the straight line has a constant gradient, and so the gradient, as it says here, is equal to K. Now, what is this K? K is what's called the spring constant. And the number that it is depends on properties of the spring, how tight it's wound, how long it is, what it's made of, those sorts of things. But it's a spring constant, and it's in Newton per metre, or Newton metre to the minus 1. All right. So Hooke's law, F equals negative Kx, is also how you might see it written. So force and extension, straight line. Now, if we want to find out the potential energy of that spring when we stretch it a certain amount. Let's have a look at a graph. Right, so here's a graph, force extension graph. Here we've got our spring constant, not spring constant, our line for the force and extension. So the gradient of that, of course, is the spring constant. Now, what we've got here on these, of course, is force and extension. So if we were to work the area out, we'd multiply those things, and so our area would get force times extension. Now, Fx, of course, is work. So as we've already known, the work done is equal to the area. All right, so let's have a look for this particular one. So for this particular one, the work, which is equal to the area, and because it's a triangle, it's a half times the base times the height. Now, this force here, it's not constant, it changes. All right, and according to Hooke, F equals negative kx. I'll leave the negative out. The reason for that is that while force is a vector, work is not. So for work it is irrelevant whether it's a negative or a positive value. And so if we then put that in there, we get half times x times kx, which when we neaten that up is half kx squared. And so the work, which is the change in energy, and in this case potential energy, and use US, U potential, S spring, a half kx squared. All right, so a little note that says there, if we stretch a spring and then put something and let it go, then it bounces up and down. So of course, as in all situations, we need to do conservation of energy. So the conservation of energy says that our total energy, we'll go to the next page, so we've got to keep in mind total energy will be the kinetic plus the potential, and in this case spring potential. All right, so if you've got something that's on a spring and it's bouncing up and down like this, beautiful diagram, then throughout that motion the total energy will remain the same, but the balance of which is what of those will change. All right, so let's have a look at an example. Okay, here's the example in your notes. A fine steel wire has force extension property shown in the graph below. Calculate the spring constant K for the wire. Now, you'll notice on this one here, part of it's straight, and then part of it goes like this. Now, back in not that long ago, there used to be a module in physics, but they're gone now, where we actually looked at the whole lot. So the bit that we are interested in is this bit. This is the Hooke's law bit. So after that we get to this point which they call the elastic limit, and after you get to that point you actually then alter the actual structure of the spring, and so it doesn't follow that Hooke's law, nice smooth straight line thingy. So if we are looking at the spring constant, then we're looking at just this straight bit here. Now the spring constant, part A, the spring constant K is the gradient. gradient is rise over run, and so if I take these two things here, so the rise is Newton, which is 40, and the run is the extension, which is 20, but it's 20 millimetres. So 20 millimetres is 2 centimetres, which is 0.02 of a metre. So our spring constant, when we do that, 40 divided 0.02 is equal to 2,000 Newton for every metre that you stretch. All right. So that's part A. Part B, calculate the strain potential energy the wire can store before permanent deformation. All right, so that's our elastic limit. So it's up to what we're talking about now. Should have used a different. So that's up to the elastic limit. So we're actually talking in this region here. So for B, if we go back here, remember 2 steps back, here we are, spring half kx squared. So our spring potential, half times 2,000 times x, and the extension there is 20 millimetres, so 0.02 squared. And then we figure that out using our calculator. So 0.5 times 2,000 times 0.02 squared becomes 0.4 joule of energy. All right. Now the last bit, part C, says calculate the work done to break the wire. So that's up to here. So the work done to break the wire, and remember we've got a force extension graph. So for C, it's the work is the area. Now we haven't got a nice, well, we've got this wiggly bit here which is not very handy. So again, we can go counting some squares. So if I count some squares, I'll go there halves. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 27, 28, 29, 30, 31, 32, 33. So there's 33 squares. And each square is 10 by 5. And the 10 is Newton, no change there. And the 5 there is 5 millimetres, which is 0.05 of a metre. And so when we calculate that, we get 16.5 joule of energy that would require, or the amount of work I should say, done on that wire to break it. All right. And so there we are, up to some text questions, and then after that there's a stack of, again, past exam questions. Again, there's heaps of them, so be selective and save others for later in the year when you are doing your revision. As always, if you have things you need clarified, make sure you ask me.